Welcome to week 2 of our Research Methods Bootcamp workshop. In today's lecture, we shall be considering sampling methods and sample size calculations. This lecture covers sampling methods and sample size calculations in research. It explains the difference between population and sample, emphasizes that proper sampling ensures external validity. We shall look at key probability sampling methods, which include simple random, stratified, cluster, systemic, and multi-stage sampling. The second part of this lecture focuses on sample size calculations for both descriptive studies, wherein we estimate proportions and means, and analytical studies where we test hypotheses about differences between groups. Formulas are provided for common scenarios along with factors that affect sample size, such as confidence level, precision, and variability. The lecture will conclude with available software tools for sample size calculations. Research often involves the observation of a sample from some predefined population of interest. Conclusions are then drawn from the study that are based on generalizing the results from the obtained sample to the entire population from which the sample was drawn. The accuracy of the conclusions will depend on how the samples were collected and, secondly, how representative the sample is of the population. Again, recall this diagram that talks about internal validity and external validity. Thus, from this diagram, we're able to see that the accuracy of our conclusions are dependent on both internal validity and external validity. We shall acquaint ourselves with certain terminology. Again, this is just to remind us of what we already know. All members of a defined group are known as a population. And we talk about parameters: mean, standard deviation, proportion. All this represented by Greek letters: mu, sigma, and pi. A sample, on the other hand, is a subset of the entire population. And when it comes to samples, we talk about statistics. Again, the mean, standard deviation, and proportion, but this time represented by lowercase letters: x bar, s, and p. A quick way to remember it is to consider that p is for population and parameters, and s is for sample and statistics. So we derive statistics from samples in order to be able to infer parameters about the population. What is sampling? This is a process of choosing a section of the population for observation and study. We use sampling when it is impractical to measure an entire population. So, for example, if we wanted to determine the prevalence of breast cancer in Nigerian women, it would be impossible to measure the entire population of Nigerian women. Sampling helps us to reduce costs, helps us to gain time, and also to reduce the amount of personnel that we need to carry out the study. The sample should be representative of the population as a whole, and the predictive power of the sample is based on both the sample size and the quality of the sampling method. What determines a proper sample? A proper sample would be representative of the population, and every variable of interest would have the same distribution in the sample as in the population from which we have chosen the sample. In order to carry out sampling, we will have to first clearly define the population, and this defined population is known as the sampling frame. How large a sample should be selected should also be considered, and then we should also determine how the individual units will be selected. The sampling frame is a list of all elements or units in the population. And examples of sampling frames include list of everybody in population surveys and list of all patients in clinical trials. In a case control study, It is a list of people with the disease and list of people without the disease. Inclusion criteria and exclusion criteria define the general framework for the population. Once the population has been identified, we need to decide how we are going to choose the sample from the population. And there are several sampling methods to consider. We have the simple random sampling, the stratified sampling, cluster sampling, systematic sampling, multi-stage sampling. In the simple random sample, the subjects are chosen from the population with equal probability of selection. This is the most common and it is the simplest of the sampling methods. One may use a random number table, or we could try balloting, or we could use computer software or programs to draw simple random samples from a given population. Simple random sampling is easy to administer and it is representative of the population in the long run. Please note that word, in the long run. It means that if the sample size is large enough, then we can have a fair measure of confidence that the sample is representative of the population. The analysis of the data is straightforward. Simple random sampling may result in a sample that is not truly representative of the population, especially if the sample size is small. Stratified sampling. When the size of the sample is small and we have some information about the distribution of a particular variable, we can select simple random samples from within each of the subgroups, that is, the strata defined by that population. So for example, if we had a population in which half of the sample were males and half were females, stratified sampling would assure us that the sample is representative of the population with respect to gender. And it would do so by choosing half of the sample randomly from males and half of the sample randomly from females. Stratified sampling can reduce potential confounding by selecting homogeneous subgroups when confounding is an important issue, for example, in case control studies. Cluster sampling. Using simple random sample in administrative surveys on large geographically dispersed populations can impose large costs and is inconvenient. In such cases, we may identify clusters, that is households or naturally occurring units, and then select random samples of these clusters to be included in the study. In this instance, every member of the selected cluster will be part of the study. And so, this introduces two types of variation within the data. We have variation that occurs between clusters. So, household A versus household B versus household C, there will be variation between clusters and households. Then we have what is known as the intercluster variance. Then we have what is known as the intracluster variance. So within the clusters, there will be some variation. And how so? If we are studying every member of the cluster, we also know that these individuals within the cluster will also have variations from themselves. No two individuals are the same. And so this is what we call intracluster variance. Clusters, on the other hand, may have certain similarities. That is to say, individuals or members of a cluster are more likely to be similar or have shared characteristics between themselves compared to members of other clusters. And so this is why there will be variation between clusters. This variation has to be accounted for when we analyze the data. In systematic sampling, the first subject is chosen at random. Subsequently, others are selected in a systematic way. For example, every fifth person may be selected after the first individual has been selected at random. It should be noted that other methods are preferred. Multi-stage sampling. In many studies, especially large nationwide surveys, different sampling methods may be used. And so we may use different methods for different groups, and we can do this in several stages. For example, in multi-stage sampling of perhaps a country, we may have the primary sampling unit, which may consist of census enumeration areas. And so we have both urban areas and rural areas, known as urban and rural strata. And so these are selected by random sampling. So in a way, this is a form of cluster sampling. And then, from the selected enumeration area, we could select households. Again, we could use random sampling to select these households, or we could use some form of systematic sampling, wherein the first household is selected randomly, and then every other or every nth household is subsequently selected. And then, from within the selected household, you can select all individuals. So for example, if we had a study that was looking at women, so within the selected households, all women would be studied. And so this is an example of a multi-stage sampling method. And this is typical of the approach used by the demographic health surveys that are periodically carried out. In contrast to random sampling methods, we have non-probability sampling. This should be avoided for prevalence studies. We often use non-probability sampling in health research. For example, patients who arrive for care become the sample. Using this approach makes it impossible to avoid selection bias. Perhaps poor patients, not so poor patients, or those who have belief in the modern health system are the ones that may present. And this already imposes a selection bias, because we have no way of knowing whether the patients we're interacting with or the participants in our study are different or similar to those who do not present at all. So one cannot know the chances that a particular subject will be included in the sample. So what is the probability of a person in Abuja coming to, for example, Garki Hospital? That is not the same for every member of the population. And we know this to be so due to a variety of factors. And so we come to sample size. The main determinant of the sample size is how accurate the results need to be. And this depends on the purpose of the study. In a descriptive study, we seek to determine a summary measure of a characteristic. Whereas in an analytical study, there are specific sets of hypotheses that we're interested in testing. Sample size for descriptive study. In a descriptive study, the main objective is to obtain an estimate of a population parameter. For example, we may be seeking to determine the proportion of people who smoke, or the average daily caloric intake of the population. The sample size required to answer these questions depend on several factors: the measure of interest, the underlying probability distribution, the sampling distribution of the measure, and the desired level of accuracy. Suppose we want to conduct a survey to determine the prevalence pi of a relatively common disease in a community. We want to determine how many people should be observed to obtain a reasonably accurate picture of the prevalence. On this slide, we see the formula that can be used to calculate the sample size for estimating a population proportion P. N is equal to P times 1 minus P times Z 1 minus alpha over 2 over delta all squared. What does this mean? The problem is to calculate the sample size required for estimating the prevalence of the disease within plus or minus 5% of the true value with 95% confidence. So we specify the parameters. The confidence coefficient 1 minus alpha is 95%. The width of the interval we're interested in, delta, is about 10%. That's plus or minus 5%. And then we make a guess as to the value of pi is equals to 30%. So if we estimate that P, the prevalence is 30%, and we plug this into the formula, it gives us a sample size of 323. And so what this means is that we need a minimum of 323 subjects observed to assure that the 95% confidence interval for the estimated population will be within 5% of the true prevalence, that is our 30% that we estimated. The above calculation assumes that the sample is a simple random sample from a relatively large population. Sometimes we encounter situations where the samples are drawn from fixed and small populations, and in which case we need to make corrections to the above formula. And so this is the correction that is effected. The DEF is the design effect, and uppercase N is the population size. Do note that we often apply this formula when the population size is 10,000 or less. What about estimating sample size for the population average? Suppose we want to estimate the average daily caloric intake of people in a community. The formula is given to us as shown on this slide. The daily caloric intake is assumed to have a normal distribution around mu, that is the true population mean, with a standard deviation sigma. The problem therefore is to calculate the sample size that is required for estimating the average daily caloric intake within plus or minus 25 calories of the true value with 95% confidence. Again, we start by specifying the parameters. So the confidence coefficient is 95%. The width of the interval is 50 calories. We obtain the standard deviation as 150 calories. And once we plug this into the formula, we have a sample size of 35. We need a minimum of 35 subjects observed to assure that the 95 confidence interval for the estimated average daily caloric intake will be within plus or minus 25 calories of the true average. How do we determine sample size for analytical studies? The primary purpose of an analytical study is to test null hypotheses. The sample size calculations require the specification of the limits of the type 1 and type 2 errors. One also has to estimate the sample measures used, a proportion, a sample mean, an estimate of the relative risk or odds ratio, and their sampling distribution. Suppose we are interested in testing equality of two proportions. The sample measures used are the sample proportions. The sampling distribution used in testing this null hypothesis is either the standard normal distribution or equivalently the chi-square distribution. And so this formula we are seeing on the screen is the formula for testing equality of two proportions. We shall consider an example. The calculation of a type 2 error or beta depends on the precise definition of the null hypothesis is not true. The simplest way to do this is to define the smallest difference in the two proportions that we consider meaningfully, that is to say clinically significant difference, and calculate beta under this hypothesis. As an example, we're interested in determining the sample size required in a clinical trial of a new drug that is expected to improve survival. Suppose the traditional survival rate is 40%, that is, P2 is 0.4. We're interested in detecting whether the new drug improves survival by at least 10%, that is, delta is 0.1, and by inference, P1 is 0.5. We specify the parameters We set the type 1 error as 0.05, and that gives us a z, one-tailed z, a two-tailed z rather, of 1.96. We determine the minimum clinically significant difference, delta, to be 0.1. And we make a guess as to the proportion in one group, usually control. Remember, we expect that it's going to improve survival by 10%. So if P1 is 0.4, then P2 will be 0.5. We determine the power required to detect this difference as 1 minus beta, 0.95. And so the Z beta is minus 1.645. Substituting these values in the equation above gives us a sample size of 640. Thus, the study would require 640 subjects in each of the two groups to assure a probability of detecting an increase in the survival rate of 10% or more with 95% certainty if the statistical test used 5% as the level of significance. What if we wanted to compare two population means? The sampling distribution of the difference of the sample means has an approximately normal distribution. The standard error of difference depends on the standard deviations of the measurements in each of the population. In the simplest and most commonly used scenario, the two standard deviations are considered to be the same. We need to determine the minimum difference, delta, in the means that we are interested in detecting by statistical testing. The two types of statistical errors, alpha and beta, and the standard deviation, sigma. Suppose we want to test a drug that reduces blood pressure. We want to say the drug is effective if the reduction in blood pressure is 5 millimeters of mercury or more, compared with the placebo. Suppose we know that systolic blood pressure in a population is distributed normally with a standard deviation of 8 millimeters of mercury. Looking at our equation, we specify the parameters. Our type 1 error is 0.05, yielding a two-tailed Z of 1.96. We determine the minimal clinically significant difference delta to be 5 millimeters of mercury, and then the power required to detect this difference, 1 minus beta, 0.95, gives us a Z beta of minus 1.645. Standard deviation is 8 millimeters of mercury. We put in these figures into the formula, and we end up with a sample size of 34 subjects in each group. What if we want to compare more than two groups? What if our analysis involves multivariate methods? The formula for these situations are much more complicated. Simple formula for the calculation of sample size are not available for multivariate analysis, such as those using multiple linear regression, logistic regression, or comparison of survival curves. This is why computer programs are available. And these are readily available for most of these cases and even situations that we have not discussed. The computations in this presentation are solely for learning purposes and for us to be able to understand the principles involved in sample size calculations. For example, for a one-sided test of an hypothesis for two incidence rates in a follow-up cohort study, here's the formula. There you go. So what software is available to calculate sample size? We have OpenEpi. This is an online web-based platform that we can use to calculate sample size. Then you have StatCalc, and then there's GPower, and then there's Stata. These are just a few of the numerous software that is available to be used to calculate sample size. The most important thing is for us to understand the principles that underlie sample size calculations, to be able to know what our type 1 error rate would be, what our type 2 error rate would be, and to also be able to ascertain what we are going to consider to be clinically significant difference that we're interested in detecting. When planning studies, one of the crucial steps is in deciding how large the study should be. And so appropriate guidance should be sought from experts.